So previously we touched on the idea that compounds from different homologous series can have the same molecular formula, they can have the same number of atoms, but they have a different structural formula. They can be arranged in a different way. And we called pairs or sets of these molecules and compounds isomers, because that was how they were. They had the same molecular formula, but a different structural formula. And in looking at that, it raised a couple of key questions. And we want to look at one of those questions in detail in this video. So we're going to talk about isomers, but we're mainly going to look at how we name different hydrocarbons that are a little bit more complex than the ones we've seen already, because they have kind of extra bits added on. So the question we really want to focus on here is, can isomers exist within one homologous series? So do I need to go between different homologous series, or can I choose one, for example the alkanes, and find isomers within that homologous series on its own? Well, let's start with a simple molecular formula. Let's just go with an alkane, and let's look at C4H10. So without this being named, what can we infer from this molecular formula? Well, we know it has 4 carbons and 10 hydrogens. That's what the molecular formula tells me. But other than that, it doesn't really tell me too much. I have to decide how these atoms are going to be arranged, how they're going to be structured, if I'm not given any additional information. So let's have a go at how we might do that. So we could, of course, draw it out the way that we learned in the alkanes video. Nice and simply, we have a straight chain of carbon atoms all joined together, and then we just make sure that every carbon in the chain has 4 bonds coming off of it to get to a valency of 4. So let's go through and make sure that this is definitely correct. So is it an alkane? Well, yes it is, because it follows the general formula of the alkanes. CN, H2N plus another 2. So yes, it is an alkane. Does it have the correct number of atoms? 1, 2, 3, 4 carbons, yep. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Yes, it does. Is it saturated? That is another prerequisite of being correct for an alkane that we need to include. Well, yes, because it's all single bonds. All of the carbons are joined together by single saturated bonds. So yes, it is. So that's completely correct. That is a completely acceptable full structural formula for C4H10. And in fact, we know this to be butane, and it's ane because it is an alkane, which all the alkanes end in ane, and we use the but prefix to show that we have 4 carbons. Great. Is that the only way that we can draw C4H10, however? Well, maybe not. Let's have a think here. If I were to take one of my carbons in this chain and pull it off, so let's say this one here, let's say I just break this bond here, pull that off, and I pop on one of the hydrogens that's left over on this pulled off bit back onto the chain to form a smaller chain. Okay, then I'd have one less carbon. But then I could just pop that carbon that I've pulled off into the middle and form a different shape. So now I've got the correct number of carbons, and they are all singly bonded to one another, but they're arranged in a different way. They're not in a straight line. They've got multiple paths. If I go from this side, I travel along, and I get to this central carbon here, I could go up, or I could continue along. I have different paths. It's almost like a branch has formed. And now all I need to do is make sure every carbon has 4 bonds around it so that it is correct. So 1, 2, 3, 4. 1, 2, 3. This one needs an extra one. 1, 2. Okay, I need another 2 here. And then at the top, I only have 1 bond on this carbon, so I need an additional 3. So let's see what happens when I populate those empty bonds with hydrogen atoms. Okay, looks a bit funky, but let's check and see if it passes all the tests that we gave this first compound. So again, is it an alkane? Well, does it follow the general formula? Yes, it does. Does it have the correct number of atoms? 4 carbons, 1, 2, 3, 4. Yep. 10 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, it does. Is it completely saturated? Does it only contain single bonds between the carbons? Yes, it is. So if this butane molecule passes all these tests and fits into that formula, but so does this one, is this also butane? Or are we going to have to come up with a naming system that is a little bit more detailed to be able to tell the difference between a C4H10 that looks like this and a C4H10 that looks like this? Because what we have just discovered is that the answer to the question is in fact yes, you can have isomers that exist within one homologous series. Because here we have a simple alkane, and the only difference between these two full structural formulae is the structural formulae. They have the same molecular formula. They are both C4H10, so they have the same molecular formula, but they have a different structure. And that is our definition of an isomer. So now that we've answered that question, we want to be able to say, well, can we come up with a better naming system rather than just make sure it ends in ane and add on a prefix? Because we've just discovered that that is not quite detailed enough to give us all the information that we need about this structure. So that's what we're going to look at next.